Okay, now let's look at some applications of quadratic functions. They do show up in a lot of real-world situations. I would say the linear functions are the most applicable and the most commonly used. Exponential is number 2. Quadratics would be number 3. So let's take a look at this, and there are several real-world applications. So one thing that we want to look at is if we take an object like a rock and we throw it up in the air, then gravity is going to make it eventually come down. Of course, it may start up if we throw it up, but then it'll reach a maximum height and then come back down. Well, if we neglect the effects of the air, objects acted on by gravity fall with a constant rate of acceleration. So this is very reasonable for like a rock or ball, like a baseball maybe, but it's not so accurate for, say, a feather or a paper airplane. But what we end up with, if we have a constant rate of acceleration, then we have a linear velocity, speed, and a quadratic function for the height. Now, actually, acceleration is not really constant. There are a couple of factors. First of all, acceleration actually decreases as you get further away from the center of the Earth. But if you're relatively close to the surface of the Earth, it turns out that it's a constant, or very nearly a constant, negative 32 feet per second square, or if you translate that to a metric system, that's negative 9.8 meters per second square. And the more important thing is the effect of the air. But if we take an object that the air has little effect on, then we get these equations. So notice that the velocity is the acceleration times time, and then we've got plus our initial velocity. And notice that v sub 0 is v of 0. Check it out. And then it turns out that the height then is half of the velocity times t squared plus the initial velocity times t plus the initial height. So this is a of t is negative 32, v of t is negative 32t plus v sub 0, s of t is negative 16t squared plus v sub 0t plus s sub 0. S sub 0 and v sub 0 are constants. The height is in feet, the velocity is feet per second, and the acceleration is feet per second square. If we do it in a metric system, the formulas are the same, except the acceleration is negative 9.8, velocity is negative 9.8 t plus v sub 0, s of t, which is the height, is negative 4.9 t squared plus v sub 0 t plus s sub 0, and the units are meters, meters per second, and meters per second square for the height, velocity, and acceleration respectively. Okay, so let's try this in a real-world example. Suppose we drop a ball from a helicopter that's 123 feet above ground, and it's traveling upward at 2 feet per second at the time we drop the ball. So our equations then become negative 32 for the acceleration, negative 32t plus the initial speed, the initial velocity. Now, by the way, the acceleration is negative because negative is the downward direction, and gravity is pulling it downward. The initial velocity in this case is 2 upwards, positive 2, so that's negative 32t plus 2. If the ball was thrown down at a rate of 2 feet per second, that would be a negative 2, but it's actually going up at 2 feet per second. So for just a teeny bit, it's actually going to go up a little bit, and then of course then it's going to reach a maximum top height and then start down, and it gets faster and faster going as it goes down. The height then is given by negative 16t squared plus 2t plus 123, because 123 was the initial height. Now this is, in the things here say run the program to figure out this, but there are other ways to do this if you don't have the program in. So how high is it at 2 seconds? Well, one thing I could do is I could just plug these in. Let me just do it this way. There's no need to plug the acceleration in, but I'll let y1 be the height, negative 16x squared plus 2x plus 123. And I'll put the velocity, in case I need it in a minute, as negative 32x plus 2. We'll put that in as y2. Now, what would be a reasonable window here? Well, t0 is when we let go of the ball. Before this, this equation doesn't apply. Negative time is fine. That just means times before we let go of the ball. Certainly, the time existed then. But these equations don't apply because other forces were acting on the ball besides just the acceleration of gravity. And I don't know how long this is going to last. This is in seconds, but let me put, let's just leave it 10 seconds for the moment. And eventually y is going to hit the ground. Once it hits the ground, the equations no longer go. And it's 123 to start with, and it's not going to go up much from that. Let's go 130, let's say. Maybe mark that off in tens. And let's take a look at the graph. There we go. We didn't need to go out as far. Looks like about 3 seconds is going to be about all the flight is. Let me make it a little bit bigger, 3.2. Let's see how that looks. There we go. And so there's a reasonable graph of the height. So it's part of a parabola, part of a quadratic. What is s of 2? We can just get that by hitting trace and doing 2. Or I could do it by hand by just plugging in 2 in the formula here. Negative 16 times 2 squared plus 2 times 2 plus 123. Or I could look at the table and look at 2. But we see it's 63 there. How high does the ball go? Well, it's going to be the vertex, which is minus b. It's going to be at the vertex, so it's going to be actually k, but h is minus b over 2a, so that's the opposite of 2 over 2 times negative 16. Let's see, the negatives cancel, the 2's cancel, that's 1/16. And so k is s of h, so I put negative 16 times 1/16 squared plus 2 times 1/16 plus 123. One of these 16s will cancel that, so this is negative 1/16 plus 2/16 plus 123. So it's 1/16 more than 123. 1/16 is, let's see, 0.0625, I think, something like that. Yeah, so 123.0625. So that's the height. So notice I did that without a calculator. Okay, but you can also find a maximum here by just doing a calc max on the calculator. Once you have it graphed, you can say calculate that maximum for. We know it's going to happen. Left one is 0, and it's not going to be very far down the line, so it's probably between 2 seconds, and I'm just going to say 0.1 is my guess. And let's see what it comes up with there. Yeah, there's the maximum. There's the x. 0.0625 roughly. Actually, 0.0625 is the exact value. And you get 123.0625 is the maximum height. So it just barely goes up a little bit, just a fraction of a foot above where it was, and then it comes on back down. When does it hit the ground? Well, what do you know about when it hits the ground? Well, when it hits the ground, you know the velocity is not 0. Some students will say, well, the velocity is 0. No, it's definitely not. Think about this. If you were laying down out there and somebody drops something on you, it's not stationary when it hits you. It's moving. So but what is 0 is the height. So you take 0 equals negative 16t squared plus 2t plus 123, and we're going to solve that. We could use a quadratic formula on that. Here on the calculator, it's pretty easy to see. We might actually want to go just a little bit, teeny bit in the negatives, so we can get just so we can see where this crosses right here. Oh, I've got some extra stuff. Oh, yeah, it's the velocity, which I don't need. Okay, and so we could just say calculate that 0, number 2. We can use a calculator technique here, if you have a calculator available. And we get over close to it. And now I need to get on the other side. And to be able to get a point on the other side, I don't know if I needed to go negative, if I needed to see the negatives or not, but let's try that for a guess. Should give you y of 0, and there's your x, 2.8358385. But if we did the quadratic formula on this, we would get that. Actually, we would get two values. One over here positive, and if you follow this on over, way over here somewhere in the negative, there's one too. But the negative one doesn't apply in the context of this problem. So at that time, it's going to hit the ground. How fast is it going at that point? So let me just stop. And that's the x that we came up with, and our y2 is our velocity. So I'm going to go to here to get y2, and then say y2 of that x that we just did. And this is the velocity. Of course, it's negative because it's moving downward. So it's 88.75 feet per second going downward when it hits the ground. So the appropriate domain on this is from when it starts, when we let go at time 0 till it hits the ground at time approximately 2.836 seconds. And so there's a graph of it. And so it's going 88.75 feet per second downward when it hits the ground. And we know what time it hits the ground. So here's another one for you to try here. Now the next one is a little less realistic, since it uses a quadratic function to model a profit function. Profit functions would typically be a bit more complicated, but definitely a quadratic model's a better model than a linear model. A linear model for profit would say if it starts here negative and it goes on up. Why is that unrealistic? Well, because this says it's going to that no matter how many you make, the more you make, the more profit you're going to make. Well, that's not always realistic, because at some point it's more likely that it may start out here and go up, and then at some point fewer and fewer people buy it, and it may actually max out. And then if you keep making them and you're not selling them, your profit's going to take a dive. Now, nobody's ever going to get over here and drive their company in the ground. If they do, they deserve to go bankrupt, because they're just making product and leaving it on the shelf and they're not selling it. That's the only way you get over there. But what we're looking for is this. We want to find this x value, which is the number of items, and where our profit, this is dollars on this axis. So we want to find this. This place where it crosses the x-axis, that's called the break-even point, and this y here is the opposite of your fixed cost. So in general, profit is revenue minus cost. So anyway, here's a formula that's given for the profit function. Can we determine some things? Well, this is our fixed cost. Actually, the positive version of that would be the fixed cost, and that negative version is the y-intercept, which is right here. If we want to find the maximum, we do the opposite of b over 2 times a. And let's see, so that's the negatives cancel. 1500 divided by 3 is 500, divided by 2 is 250. So that would be right here, 250 items. And we plug 250 in here and see what the y turns out to be. I could do it by hand, but I probably would rather do it on a calculator. And we can get that maximum amount. It turns out that $250 items right there to maximize the profit. and the maximum profit turns out to be this. That's the y-coordinate. This is k, y-coordinate of this vertex. And the h, the x-coordinate of the vertex, is the number needed to maximize the profit. So I could graph this on the calculator and just calculate these different things without using any of these shortcut formulas that we've learned. The calculator has very nice approximation capabilities. So in fact, I could just use that on here. Okay, just graph it, do a calc max here, do a calc root for the break-even point, which is 10.7 items. It's called break-even because the profit's equal to 0. Well, profit is revenue minus cost. Revenue equals cost, so these are even. They're the same as each other, what it means, break-even. Even revenue and cost balance each other, they're the same. That gives you 0 profit. So over here where you've got a positive profit, this is a gain. And when you have a negative profit in there, that's a loss. And typically you have some startup costs, which are the opposite of that. These initial costs are fixed cost, and then you have to start, you're charged a certain amount there regardless of how much you make. And then as you start making more money, making more items, you're selling them, making more money, you eventually break even and then hopefully going up. And you want to stop right up there at the maximum amount. So that's a kind of a reasonable looking formula, although it may be more complicated looking than that in a reality situation, but that's a much more realistic thing than a linear. Another thing that happens a lot of times is areas turn out to give you quadratics. In fact, the name quadratic, you may have been wondering about this. Quad sounds like 4, and yet what we're talking about here is exponential. What we're talking about is these have an exponent of 2. In other words, second degree polynomials, and yet we call them quadratics. Well, why is that? Well, look at what happens if you've got a quadrilateral. If, say, one side is x and the other is, say, x plus 1, what's the area? The area is x times x plus 1. That's a quadratic. Also, why do we call something squaring? Well, it's the area of a square. If that's x and that's x, that area is x to the second power, which is x squared. So, these are finding quadrilateral areas. So, hence the term quadratic functions. So, a lot of times geometric problems with areas will result in some quadratic functions. So, here's a thing. We have a river going along here. Okay? So, there's no need for, but we're going to build a fence. We build a fence on this side, and this side, and this side, and we're going to maybe keep some animals in there or something, and we build a fence here. Now, apparently these are some kind of animals that aren't going to swim off, but they can go to the river and maybe get a drink or something. And so we're going to fence it in like that. Make rectangles. Well, we have 600 feet of fencing altogether. You're going to have x here, and x here. And so then whatever's left, maybe we'll call it y here. We know y plus 3x's has got to be 600. So y is 600 minus 3x. So that's what I have here. So what's the area? Well, base times height. So the total area we have enclosed in this big rectangle is just x times 600 minus 3x. So right away, we've almost got it in a factored form. We factor out a negative 3x, and we do. Negative 3x times x minus 200. Or we could expand it out, negative 3x squared plus 600x. Different forms we could put it in. And so if we want to maximize the area, we need to find the vertex. And we could do it a couple of ways here. Here we can see the roots are 0 and 200. So if we just average those, of course we get 100, and that's our h. Okay? And so that's going to be the x value that's going to make the width. See, this is a negative, so it's we graph it as a parabola. It's actually when x is 0, you get 0. When x is 200, you get 0. When x is 100, you get it to max out. So it's definitely opening concave down. X has to be somewhere between 0 and 200 to make this to work, because you can't have a negative x, because it's a length here. Can't even have 0x really. So 100 is going to be where this thing maxes out. What would it be? Plug in this. It's negative 3 times 100 times 100 minus 200. So that's negative 100. Got a couple of negatives here. Cancel out. And so this is 3, and then we got 4 zeros. So 30,000 square feet is what we have. And you can check it out. You're going to have 100 here, 100 here, 100 here. So that's going to be 300, and that leaves 300 here. And so you got 300 times 100 is your total area, which is the 30,000 square feet. So area, here's some basic area and volume formulas. The area of a parallelogram is base times height. Triangle is 1/2 base times height. For a trapezoid, it's the average of the two bases times the height. A circle is, this is supposed to be pi times the diameter for the circumference, or 2 pi times the radius, and this should be pi r square. I'll just fix the font there. Actually, let me just do that. It'll take me just a second to make that look right. That should be, let me just go with the symbol font here. And there we go. And let me just copy that, paste it over. So that's pi. And the area is pi r square. If you got a circular sector, it is r times theta. Yeah, something's out of whack there. I'll have to figure out that a little bit later. And this is pi. If you have an ellipse, a stretch circle has a kind of neat kind of formula. One of these lengths is A, and the other length is B. And if you multiply them together by pi, you get the ellipse, area of the ellipse. Of course, if the ellipse degenerates to circle, both of those are the same as r, and of course this becomes pi r square. On a prism or cylinder, you find the area of the base here, and then you multiply by the height here. For a cone or a pyramid, you find the area of the base times the height, but then you multiply by 1/3. Okay. For a sphere, the volume is 4/3 pi r cubed. There we go. And the surface area is 4 pi r square. And I don't have time to derive all these different things right now, but those are some formulas you might remember from, maybe from a geometry course in high school or or junior high school or somewhere along the way. You might have seen those before. If not, you have reference here. And here's some different problems that are kind of like the ones that are above. So, and a few others that are variations. So I'd like you to go ahead and try to work those out. And then I got a couple more parts of this video series, so we'll come back and pick up here next time.